Good afternoon, everyone. It's my honor to be here to share with you my learning or exploration of the calculation of the volume of the n-dimensional sphere. For the motivation of it, Professor Chi-Kun Lin, Andrew Lin, once mentioned the calculation of the volume of an n-dimensional ball in his Wednesday evening class, emphasizing that when we are young, we should practice hard calculation skills to make our research time longer. And also, Dr. Chi-Kun Fook, in his 2015 slides in his website, stated that the calculation of an n-dimensional ball is not complicated and is a good representation of how to use the iterative method to make the calculation of this more concise. And he also mentions the idea of the calculation of Gaussian integral to calculate the n-dimensional sphere. And I used to think that the calculation of an n-dimensional ball could only stay in my appreciation of the beauty of the iterative method and my understanding of the Gaussian distribution living in two-dimensional space. However, when I opened the page on high-dimensional statistics, written by a very famous books about high-dimensional statistics, I also see it. I realized that the beauty of mathematics actually has meaning in statistics, which makes me feel the world, the statistic world, the mathematics world is actually interesting and charismatic. Now let's begin with the calculation of the Gaussian integral, which is the motivation of today's topic. We know that if we want to calculate the Gaussian integral, we could not just write one integral because it's living in the two-dimensional space. So write it as a double integral. When we write the double integral, it has its natural advantage, which is we could write it as the sphere coordinate, which is the polar change of variable. And this step is the most important idea of the calculation. Now we begin with the topic of the day. Firstly, we define the space of this we just regard r equals to 1 just now. And v and I equals to the volume of n-dimensional ball of radius r. Now we know that we define the n-dimensional ball's volume as this. And when we want to just write it as the xn instead of from dx1 to dxn, could draw a picture. X, Y, Z. Now we like to integrate this ball. We already have this circle, and we just regard D as the where xn comes from. Let this be xn, and we want to use just the xn to represent v and 1, and we want to integrate the circle. This 1, this xn, so this is 1 minus xn squared. So here we just write and we want to further represent it. So we want to use v minus 1 1 to represent it, since this is very easy to calculate, right? So how to calculate this? We just want to want to know the relationship between v and r and v and 1, and what's the coefficient of this. Firstly, we would like to use the pi r form, per square, and the sphere is, so we guess it's just r power n. So what is this true? Now we make it more rigorously. We write v and r as more rigorous way using integral. This is a big measure, and this indicator function is just and here it's just like that, and that becomes to r. Now we like to use the knowledge of the transformation of variable using Jacobian matrix to make a change of variable. Now we write y equals to r we get we need to have a determinant and then times the Lebesgue measure of the n dimension with y, with corresponding to y. Now what's this? Now let's recall our knowledge of the Jacobian matrix. This is just like which is just, you know, another write the whole form of it is like that. So this will become, this will be equals 0, this 0, this 0, this will, this leads to x1 equals to ry1, x2 equals to ry2. So the diagonal of this matrix is actually LR, and the other are L zeros. So this just the RIN, where IN is just the identity matrix with the dimension of n. So it just equals to this is actually the proof of this. Our guess is true. Now we continue. So we know this just and we could continue write it as but this method is actually a little bit complicated, so because we could never, right? So we need to find a more general iteration method. Now let's consider this and recall our motivation, the idea of the calculation of the Gaussian integral. And we just write it as the double integral. How could we write it? First, we know that is the like that, right? Now we want to look at this coordinate with this to be xn minus 1. Now what we have is this equals to 1, and we want to integrate the whole area of it. So firstly, we know this is xn, this is 1, and here and so this minus. So firstly, know this integral is from minus this to the positive this, and we integrate from minus 1 to 1. So it's just and this actually right? Actually, this is the forbidden theorem. Okay, let's continue. We have double integral, and these square things, just like the Gaussian integral calculation duration process, we just change of it at the the polar coordinates. Now let's do this. We use the knowledge of just now. Now it's a good idea to make another change of variable. Actually, this is a constant which could be moved outside, but it's not important. Now, we know a very important iteration, which is followed by that. This is just which is actually this, because which is just equal. So we finished our proof of this. And actually it could be right as this is gamma function. This is actually the topology